And all of the later chips from ChipCon behave in a similar manner and are derived from the same design. There is now competition from Atmel and Ember and a few different manufacturers for these chips. And most importantly, you have sensors so that it can see something. And whether the sensor is trying to detect party mode or the temperature sensor on the temperature on a chemical vat isn't terribly unique to the platform. So here you just have two spaces for transistors, like phototransistors or a temperature sensor, and you can just solder them down and swap things out. And they also support extension boards. So if you want to build your own, say, party mode device, and you don't want to make so many of them that you have to fab your own board, you can just use the connector on the end, plug it up, and have it work. The operating system is designed for wireless sensors, so it uses a component-based architecture. The idea here is that you have different modules, which are almost like C modules, except that they're wired together. So you have classes, but those classes are instantiated at compile time rather than at runtime. You don't have enough RAM to do anything at runtime. So all of your executable code remains in flash memory because that's necessary, and you can't declare classes at runtime and then have pointers going back to it. It's all too slow and it's too bulky, and then your stacks grow too large. So instead, you have a preprocessor that takes all of this complicated class-based code and spits out a single C file of spaghetti code, which is then compiled to run on the device. And it uses tricks like automatic function inlining to try and shrink your code automatically. And then it's task and event-based. So instead of having a while loop, you have events which trigger a particular handler function. For example, you might make a timer that expires every 15 milliseconds and does something. Or you might perform an event whenever the radio receives a packet. And this is all tied into power management. So it can see that there are no, let's say you're not listening to the radio and there are no events to be triggered for 500 milliseconds. Well, it can then know that it's perfectly safe to sleep for 450 milliseconds, and then you saved a half second of power consumption. And there's only one application per device. It's not a PC where you copy an executable file separate from your operating system. The two are compiled and linked together and form a single C executable. There's no preemptive multitasking between processes. There's no memory management or memory mapping. Every function sees the same arrangement of memory and can even read and write I/O devices directly. It comes with several applications. So when you're trying to port it, you can port to the blink application first if you only want the lights to blink. But that's not as simple as running a while loop and blinking the lights because that would kill your battery. So instead, there are 3 LEDs blinking by 3 separate timers, and there are no hardware-specific functions. So if you have a working port of the operating system, you should be able to compile this so long as your basic C compiler is working, your scheduler is working, your power management is working, and your timers are working. So the idea is that with each application that's just a little bit more complicated, you tell that more of your port is working. So you can run this before you get the radio working, or even before you get the serial ports working, as those are more complicated to write than simple scheduling. Its Makefile just specifies the main component and then includes make rules, which is referring back to the operating system itself. So you source a shell script, which sets this environment variable. The code itself defines components by name, and then it wires them together. So like it's specifying a handler function for booting and then for each timer. And it's also bringing the global LEDs component in. And then these are also instantiated inside of the module. And then the handler functions actually determine, say, how often a timer runs. There are no parameters that are passed at the time that you're instantiating the function. So the 250 millisecond, 500 millisecond, and 1 second timers are all specified separately in a startup function. And when you disassemble these, you can actually see that the startup function runs before the scheduler begins firing events. So you can make sure that everything's together without having to handle full compilation and that sort of stuff. You can compile this to run on hardware. and you should be able to compile it on any hardware that has a TinyOS port. But you should also be able to run it in a simulator. So they have a simulator that comes with TinyOS that allows you to compile for POSIX processes. So you can run 600 copies of the belt buckle and make sure that the mesh networking works between them, all virtually before you actually have to field anything. And that way you don't have to have 600 laptops with 600 JTAG adapters trying to spy on variables inside of each of those nodes. And you can avoid all of that and do everything in simulation, make sure that it works there, and then also make sure that it works in hardware. And when you compile to hardware, it's vastly different hardware. Some of these chips are 8-bit, some are 32, these are 16. Some are von Neumann, some are Harvard. They use different compilers. There's all sorts of variation in it, but it's all handled by a single Perl script, rewriting your C code, spitting it out and compiling it, and importing the proper modules. Other standard applications include a base station, which is like a primitive packet sniffer designed to allow you to connect your network up to a PC, but it doesn't support channel hopping or anything else that you would want in a more complicated, dedicated packet sniffer. It has a radio sense to LEDs program, which is really cool to play with because you can have 2 units, and the LEDs of one unit will display, say, the light on the other, and then you can cover one up with your hand and you see the other one instantly respond. I modified this to do signal strength instead, and then if you move your hand through it, you can actually see how the radio signal degrades in signal strength, not in bit quality, when you move your hand through. And so you can play it sort of like a theremin, and move your hand through and then out. And then there's a multi-hop oscilloscope, which actually sets up a mesh network and then relays the temperature at each point to you. So if you wanted to use these in, say, a commercial product,
one good application suitable for this audience is imagine each of these seats had a mote in them, and this mote could relay back to some end user which seats are currently being occupied. That would just be a useful way, perhaps, for someone to monitor that and make sure someone's not occupying the seat when they're not supposed to be.
I mean, if you've ever been at a conference with like surveys that you can fill out to specify how much you like to give and talk, how many of you actually fill those out? And how representative is that of the audience? If instead you could determine like exactly how many people were there at the beginning of the talk, how many left early, how many were there at the end, then you could get a better metric of it, and you want to have that slanted toward the people who like to fill out surveys. You can also monitor steam pipes to figure out like, where steam is being lost in industrial heating. Because if you've got, say, university being heated by steam, you're losing a lot of money by the steam that's spilling heat out through vents. Finding it is terribly difficult. You've got to have people climbing through tunnels to check it manually. With this, you can just make sure that there's water in the steam trap. If it goes dry, you know that it's leaking. You can do manufacturing, soil monitoring, and all of that stuff. But the most important application, and the one from which we've benefited most personally, is party mode. And when you've got party mode, there's this thing going around, it was very popular in Berlin, pant status. So we'll be getting to pant status soon enough, okay? But the idea is that once you first have this idea of a board, the idea is enough to get people excited, you know? And then you get the board itself, and then you can start soldering them together, and then you get the software for the next one, and you can do the demo with the radios, and it's loads of fun. And that's the whole point of this, becoming a belt buckle engineer instead of just a boring engineer, you know? Belt buckle, right? So when Josh came up with his original idea, we started taking it out to the bars. Extra neighborly, you know? And neighborliness just abounds. It's everywhere. Everyone has to be a neighbor. And when you take this out to a bar, you can just meet people and say, hey, be a neighbor. And that's how Josh lost his virginity. We brought this out on a Thursday, and by Saturday, he was a man. Okay, but this doesn't come without work, you know. So first, you have to lay out your board in a CAD Design tool. You can download the free version of Eagle, and you can start laying out boards with it. It's not quite sufficient to do the radio boards, which need to be 4-layer for all sorts of annoying reasons. Now, once you've done the CAD design, you simply ship off your CAD description, called Gerbers, in a standard format off to China, and you pay them $100, $120 by PayPal,